Hi guys, so today we're going to continue our Algebra 2 review and we're going to look at complex numbers. Now if you guys remember, these are the i's and the imaginary numbers. So you learned about this in Algebra 2, so the basis of this is that I is equivalent to the square root of -1. So we know we can't take the square root of a negative number because there aren't any two numbers that multiply to give us a -1. That's why we refer to it as I. So if I is equal to the square root of -1, then I squared is -1. I cubed would be a negative square root of -1, and I to the fourth power would just be a positive 1, because it would be -1 times -1. When it comes to operations with complex numbers, it's actually not too bad. Basically, whenever you're adding or subtracting complex numbers, you keep the real part together and you keep the imaginary part together. A lot of times our goal here is to write these in the form of a plus bi, where a is the real part and b is the imaginary component. So we basically split up the real and the imaginary. So if you look here at this first example, I have my two real numbers. I've got 6 minus 2, so I can go ahead and combine those. And then I have 3i minus a negative 2i. So remember that negative does go to both terms, so if I make that plus, that becomes negative and that becomes plus. So I have 3i plus 2i, which gives me 5i. So I can simplify that into 4 plus 5i. When you're multiplying, even though you can't add them together, you can multiply them all together. So I'm going to FOIL this out, so I'm just going to multiply every term by every term. So 6 times 2 would give me 12. Then I have a minus 12i plus 6i minus 6i squared. I can combine the imaginary parts together, but more than that, knowing that I squared is a -1, I can actually turn that -6 into plus 6. So now I have 12 minus 6i plus 6. I can again combine the real parts together, and that gives me 18 minus 6i. Now dividing kind of incorporates both multiplying and adding. In order to actually divide complex numbers, you're actually multiplying by the complex conjugate. So we talked about conjugate a little bit when we did our proofs. So if we had 1 minus cosine x, we multiplied by 1 plus cosine x to get those middle terms to cancel. Very similar with the complex conjugate. I'm going to multiply by what's on the bottom, but I'm going to multiply the conjugate of that. So instead of 6 minus 4i, I'm going to multiply the top and bottom by 6 plus 4i. And the reason I'm doing that is because when I multiply by that conjugate, those middle terms, I would get minus 24i plus 24i, they cancel out. So that's the reason I'm choosing to multiply by that value. So what that's going to do is at the bottom, that's going to give me 36 minus 16i squared, but as we just saw in that previous example, 16i squared actually becomes a negative 16. So now I have 36 plus 16, which gives me 52. Then to do the top again, I'm just going to FOIL that out, multiply everything times everything. So 3 times 6 would be 18. 3 times 4i would be 12i. 2i times 6 would be another 12i, and then I would have plus 8i squared. So I would get 18 plus 24i minus 8, which would give me, I left off an I, I'm sorry, which would give me 10 plus 24i over 52. Now if I want to split this into that a plus bi form, remember both of those numbers at the top are being divided by 52, so I can split that into 10 over 52 plus 24 over 52i. Then I can just simplify those two fractions. So 10 and 52, they're both divisible by 2, so I can reduce that to 5 over 26. And then 24 over 52 I can reduce as well, but that one's actually divisible by 4. So I could reduce it a little bit further if I wanted to 6 over 13i. Now when it comes to square roots of negative numbers, one thing to be careful of, if I do the square root of -2 times the square root of -5, it'd be really easy for me to think that that value would actually be the square root of 10, because I would just multiply those numbers together. What's important when you're multiplying those negative square roots is that you actually take that negative out and replace it with an I. Okay, so if I rewrite this first as I times the square root of 2 times I times the square root of 5, that gives me I squared times the square root of 10, and I squared is actually a negative square root 10. So what that means over here, if I would actually be multiplying some of these square roots together, it may help if I replace them with i's first. So what I'm going to do is I'm going to replace this with the square root of 3 minus 2i, and then I have the square root of 6 minus 2 root 2i. Or let's leave it as square root of 8 for now, just to make it a little easier to multiply. So I'll call it square root 8i. Because anytime we have a negative inside the square root, a negative inside the square root is equivalent to an I outside of it. Now I can go ahead and FOIL this, so I can get root 3 times root 6 would be the square root of 18. Root 3 times root 8i would be a square root of 24i. Then I have minus 2i times the square root of 6, that would be minus 2 root 6i. And then I have plus 2 square root of 8i squared. Now the simplifying here gets a little messy. I'm not as concerned with you guys getting this all perfect. I really just wanted you guys to see the difference that you can have when you have that square root inside and changing it to an I outside. But I'll go ahead and finish this up. Square root of 18 reduces to 3 root 2. Square root of 24 reduces to 2 root 6i minus 2 root 6i. And then this would become minus because of the I squared. So I have minus 4 root 2. So if you really wanted to combine these together one step further, you could with negative root 2 as your real part. That would be 3 minus 4 root 2. And then minus 4 root 6i. Now don't you guys get too caught up in all the rational stuff there. I know some of that can be a little bit confusing. What I really just want you guys to understand is if you have that negative, making that I first. So the last thing we're going to do, it's going to be more applicable to what we're going to be doing with our real numbers and our finding all zeros, which we're going to do next, is taking a function that's quadratic or something else along those lines and realizing it may have zeros that aren't actually real. So for example, if you have a quadratic function that looks something like this, we're not going to find any zeros to that function by factoring or any other way because it doesn't actually cross the x-axis. But that graph does have imaginary zeros. Now what's nice about imaginary zeros is they always come in pairs. So for example, if 1 plus I is a 0, then 1 minus I is also going to be a 0. And what we're going to use most often to find our imaginary zeros, or to find all of our zeros if we're unable to factor, is use the quadratic formula. So what we're going to do is set this up with the quadratic formula because I know this can't factor. I don't know any numbers that multiply to 14 that add up to 6. So since this won't factor, I'm going to use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. So this becomes negative 6 plus or minus the square root of b squared, which is 36, minus 4 times 2 times 7, all over 2 times 2, which is 4. And then I'm going to go ahead and simplify this a little bit further. So I have negative 6 plus or minus, and then I've got 36 minus 4 times 2 times 8, which would be 36 minus 56, which would be a negative 20 over the square root of 4. And at this point, hopefully it's clear to you guys this will be imaginary because I can't take a square root of a negative number. What I can do though is go ahead and simplify this and write it in terms of I. So what I'm going to do is I'm going to go ahead and, before I even simplify square root of 20, let me write this as negative 6 plus or minus I times the square root of 20. Because the I is equivalent to the negative inside the square root. If you take that negative out, just make it an I on the outside. And then the square root of 20 I can simplify as well. And that becomes 2 root 5 times I. Now if you want, you can simplify this a little bit further, and you can simplify it in two different ways. I can divide everything here by 2, because the bottom number and both top numbers are divisible by 2. I also could write this in that a plus bi form. I'm going to go ahead and write it that way just because that's very similar to the way you may see an answer choice or something like that. So if I split this up, I could have negative 6 over 4, which I'm going to go ahead and simplify to a negative 3 over 2, plus or minus And then I have 2 root 5 over 4, which simplifies to root 5 over 2i. So I do have 2 answers there. I have negative 3 over 2 plus root 5 over 2i and negative 3 over 2 minus root 5 over I. So those will always go in those pairs.